in the first place. It's a great chance to get back to India for the first time in about 5 years or so. So thank you so much indeed for coming along. This talk is all about resilience, and I'm looking in this space mostly because a lot of people are building distributed systems, whether they should or not. The reality is we are building them, and so this talk is really trying to get you all to think, okay, now I'm building a distributed system, how do I make those systems as resilient as possible? This isn't a talk about deep technical details. This is looking at the breadth of what resiliency is, to get us to think differently about how we make our systems resilient. That word systems will come back a lot. What is a system? So I'm going to give you a bit of high-level theoretical backing for what resiliency and resiliency engineering is. And I'm also going to give you some practical, here's some basic building block things you should be doing as well. I'm doing this partly, this talk's come a bit from the research I'm doing around my new book. My new book is not out. It will be out, I mean, if I was not here, I'd be writing the book, but I'm not, I'm here. So this will be going out next year, but you can read an early access version of this later. There'll be more details about how you do that later on. I'll also give you a QR code at the end if you want to download all the slides for this talk as well. Feel free to take photos if you want, though. We're going to be talking today about what is resilience, because there are different definitions out there. I'm going to use my one, and therefore it is the best one, because I'm the one speaking right now. We'll talk about what resilience is. We'll talk about what resiliency engineering is. We're then going to look at 3 different models for exploring resilience engineering, and we might also even talk about what these folks have to say about resilience as well. So let's start at the beginning. What is resilience? The first thing to say is that resilience is not something you have. It's not like a binary property of a system. You don't either have or not have resiliency. It's not like flicking a switch. Resiliency is a property of how a system performs. It's much closer to our concept, therefore, of, say, quality, right? We don't say a system has quality, we say how much quality does it have, and we have our own definitions about what a sufficient level of quality is. I'm going to now use quite a wordy definition for resilience that comes from a person called Eric Holnagel, who's one of the sort of founding lights, I guess, from the academic space around both safety management and resilience. And it's a big quote, but I'm going to break it all down. So this is Eric's definition of resilience. A system is said to perform in a manner that is resilient when it sustains required operations under both expected and unexpected conditions by adjusting its functioning prior to, during, or following events. So we're going to break this down a little bit. But I think it's actually a good definition. So we start at the beginning, right? We're going to talk about this idea of sustains required operations. So there is this idea that when we are saying that something is resilient, we need to say, okay, what still needs to happen even if something goes wrong? Right, so something goes wrong, there are certain things we still need to be true about our system. So we actually need to quantify those things. What are those things that need to be true when something goes wrong? So if you think about like air travel, I flew here, so this is what I'm thinking about, is I flew here on a plane, I didn't walk, right? We think about airplanes, right? Jet planes, they have more than one engine. Right? We know this because if one engine fails, we still need to be able to land people safely. The sustains required operations part of air travel is people need to be safe. So if things go wrong, we may not get to our destination, but we're going to make sure that people are safe. That's how these things are built. So the sustains required operations for air travel is people need to be safe, right? That's the thing that has to be true. So then we've got this idea of dealing with both the expected and unexpected. And this is a bit of an issue. A lot of organizations create their systems in such a way to deal with the expected, but they have no ability to deal with the unexpected. So this is us being prepared for both the known and the unknown. And then finally, we've got this idea that a system, to be resilient, needs to adjust its functioning. And this is a really important idea as well. Something isn't resilient if it tries to do everything, even when things are going wrong. That can actually make a system more fragile. We have to accept that when things go wrong, there may be certain things we stop doing in order to protect the wider system. So again, this comes back to this idea that you need to define what are the things that have to still be true, and also accept that there are some things you're okay to trade off when things start going wrong. Okay, so that's really clear. So When things go wrong, the system might need to work differently. This is where we get into concepts like graceful degradation of functionality, for example. So we can sort of summarize this idea of resilience down to being able to ensure that certain operations continue to work even when things go wrong, right? So that's our definition of resilience. Let's go to this concept of resilience engineering. And this is an emerging field that's kind of been around for several decades now, and it's been kind of widely understood in the areas of sort of safety critical systems, but we don't necessarily embrace these ideas, I think, very fully in the majority of the software we build. So to explain what resilience engineering is, we should probably also look back towards what came before, which is what we think of as traditional safety management. And safety management is all about reducing adverse events to reduce adverse outcomes. So the idea here is we don't want something to break. So if we allow a component of our system to break, that might lead to a bigger problem. And so with traditional safety management, the focus is on making sure that nothing goes wrong. So this is where you kind of have this culture of there's been 0 days since an accident and this factory type things going on. The problem with this model of trying to make sure that nothing breaks, that nothing goes wrong, is it really does struggle at scale. And if we think about the systems that we are building, the distributed systems, especially when we're building things for India scale, we have a lot of things. So let's look at this from a mathematical point of view. If I have a single component in my system, and that component on any given day has a 1 in 100 chance of failing, then that means on any given day there's a 1 in 100 chance that component may be broken. If I have 3 copies of that component, all with the same failure rate, the chance on any given day of one of those components having been broken is now just under 3 in 100. Now, to my brain, it should be exactly 3 in 100 chance. My wife has explained this very carefully to me because she understands maths, I don't. It's not quite 3 in 100, but it's close enough, all right? So it turns out that maths is actually quite hard. So, but the kind of idea here is, as we increase the number of components, the chance of failure of a component on a given day is going to increase. So the more components we add, the probability of there being a failure on any given day increases to the point where the failure of a component on a specific day is almost inevitable. So if I had 100 components, the probability of there being a failure in one of those components approaches 1. Again, not exactly 1, but you can look it up online. So we've got this issue of scale. As we have more things, it becomes increasingly difficult to ensure that none of those things fail, just purely from a mathematical point of view. And then we also have to accept that our systems are messy. And we'll be looking at one of our models later on that shows us just how messy our systems are, because they unfortunately involve, often the weakest link, humans. So we had this idea of safety management, which was trying to ensure that a single component would never fail. And what's emerged out of that work is now what we refer to as resilience engineering. So as safety management was all about trying to ensure that nothing ever went wrong, resilience engineering takes a different stance. With resilience engineering, what we're trying to say is we want to make sure as many things as possible go right. And this is a very different mindset. We want to make sure as many things go right as possible, with the caveat that we're going to be able to continue operating even in different situations. Traditional safety management is often brittle because we say we don't want anything to break. But if something does break, we are unprepared. With resilience engineering, it's like we accept that things might break, but we still want to keep operating. So with a safety management point of view on, I'm going to try and stop a component from failing. So I think about a computer. What's most likely going to fail in a server? Things are moving parts. So the power supply. So if I'm worried about a power supply failure, taking out a server, I'm going to run a system with redundant power supplies. Quite a common thing to do when I was still doing sysadmin type stuff. You'd have servers which have 2 power supplies in them. And you'd have redundancies in the racks and stuff as well. Because when you have a small number of components, with a very small number of components, it does actually still make sense to reduce the chance of that component failing. If you've only got 1 computer, then actually spending extra money to ensure that computer has less chance of failure is valuable. decreasing that failure rate to being 1 in 100 to 1 in 1,000 might be worthwhile from a point of view of the money you spend on it. But as you have more and more components, it becomes maybe not as sensible to try and decrease the failure rate of an individual component, because even if you can reduce it by 1 in 100 to 1 in 1,000, you've still got so many things that failure on any given day is still inevitable. So we have to be prepared for what happens when things go wrong. So if computers fail, we start thinking about building systems that don't care. I think one of the best concrete examples of this comes from Google. This is the top of, this is actually a Google server. This is from about 15, 20 years ago. And you might think, oh, they've taken the top off this case so that we can see inside to see the internals. No, 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 there is no case. This is how it goes in the rack, right? You also notice other interesting things. This stuff here that's connecting the 2 spinning platter hard drives and the power supply, that's Velcro, not screws, Velcro. There's a recognition that the things that fail most frequently in servers are, again, things with moving parts. So the spinning platter hard drives, the power supply unit. They've got so many computers, even if they had low failure rates, they still have some computers failing. So they built software-based systems that don't care, and they also built their server racks in such a way that they can be rapidly replaced. So someone would come along in the morning, look at all the machines that had failed because a hard drive had failed or a power supply would fail. They'd pull the rack out, rip out the Velcro, put the power supply in the bin, put the hard drive in the bin, get another hard drive, stick it in, push it back in, turn it back on again. And by doing this, they made it very quick to get that machine up and running again, and they could also use fairly cheap components as well. This is actually a different view of one of their racks. This one is actually in the Computer Science Museum, the Computer Museum in Silicon Valley. I think there's also one of these in the Science Museum as well. This is a different mindset. We're not trying to make this individual computer really resilient. We're trying to make the whole system resilient. The way to think about this, though, is that resilience engineering isn't about saying safety management doesn't matter. It's about saying that safety management by itself isn't enough. So the concept of stopping bad things from happening is still probably a good idea, but it may not be the only thing you should focus on. So resilience engineering encompasses all of that and more. So what we're going to do now is we're going to take a look at 3 models that help us explore this notion of resilience and resilience engineering in different ways. So the 3 models we're going to be looking at cover a whole gamut of things, but I'm going to preface all of this by giving you a bit of a quote from George Box, the statistician, who said that all models are wrong. And we often add on the other bit of information, but some are useful. These models are not foolproof. They don't combine together to form some kind of Ultron model or whatever. They're all useful different ways for us to look at and explore the notion of resiliency, but they'll have their flaws here and there. So we're going to be looking at Woods' 4 concepts for resilience. We're going to be looking at the Dickinson hierarchy of service reliability, and you try saying that 10 times quickly. And we'll also be looking at a hexagonal model for socio-technical systems. Let's start off with Woods' model, which comes from a paper that the unfortunately now late David Woods wrote many years ago. And this was actually a paper that started me on this journey. I read this about 10 years ago, and I can't understand anything in this paper, right? Literally, it's really difficult to understand because David Woods was talking about resilience engineering in the broadest sense. He wasn't talking about our digital systems or even our computer-based systems. This paper looks at the notion of resilience engineering as it applies to everything. Biological organisms, states, hospital management, air travel. So it's quite generic and quite academic and therefore quite hard to read, but I do urge you to give it a read if you really want to go deep into this topic. In this paper, Woods outlines 4 concepts for resiliency, which we're going to look at. He talks about robustness, rebound, graceful extensibility, and sustained adaptability. So we're going to look at each of these things in turn and sort of try to understand how they apply to us in our digital systems and the things that we build today. So let's start with robustness. So what is robustness? Robustness is our system's ability to handle known adverse events. So we have an understanding about the things that can go wrong, and we build our system in such a way to handle those known issues. So this is how well can we handle the expected. So coming back to the airplane example, we have two engines because we recognize there are circumstances in which one engine might fail, a bird strike being a great example. So we know we have more than one engine so that we can still land safely. If you're thinking about a simple service-based architecture, we recognize that a single node can fail for a host of reasons, a power supply failure, for example. And so we would have multiple copies of a service and some kind of load balancer to distribute load or some other load distribution mechanism. This is us thinking in terms of robustness. We recognize that a single node may fail, and so we build our system in such a way that we can have more than one copy of that. And we make architectural choices accordingly, because if one node fails, we hope that the rest can handle the continuing load. This actually introduces one of our more interesting challenges around resiliency. As Woods puts it in the paper, expanding a system's ability to handle some additional perturbations increases the system's vulnerability in other ways to other kinds of events. So when Woods talks here about perturbations, he's sort of saying we're kind of increasing the complexity of our system to handle new events. So we think this could happen, so we add something to deal with that issue. So we're adding like a load balancer and the ability to spin up multiple copies. But fundamentally, we then have a challenge that if we increase complexity to improve robustness, which is kind of what we've done here, that can lead to more sources of complexity. Like this, for example, which is the kind of common stack you might get for a Kubernetes-based system. At every level, we may have made a completely sensible decision in isolation, but when we step back, we think, what unholy mess have we unleashed here? And all of this now is increasing our surface area of potential problems. And this is a bit of a challenge that's not sort of kind of, we can't solve it. We have to be aware that this challenge exists. Let's move on now to looking about rebound. This is our ability to recover after a traumatic event. And again, this is often where safety management wasn't really being handled well. Something goes wrong. When something goes wrong, how easy are we able to recover? So we think about the airplane example. We've taken off. We're trying to go to somewhere that's nice for our holidays. We've hit a bird. It's bad news for the bird. The bird's not recovering. I've got to be honest with you about that. The engine has failed, but the plane still has another engine. So that's a traumatic event. What's our recovery? Our recovery is getting the plane back to the airport. We're not still going to try and fly for holiday, although I'd like to go on holiday. It's better we're safe, so we just get back to the airport. That's part of our recovery. It's dealing with the trauma that our aircrew may now have suffered after having that accident. It's getting people rebooked on a plane. So when you think about your own systems, do you know what you're going to do when something goes wrong? How are you going to handle that? And how are you going to get back up and running? So that's our concept of our rebound. How quickly can we bring back a missing service instance when it fails? Things like desired state management here can help. If a service is offline, how quickly can we get that service back up and running again? Let's move on to our third concept from Woods' model, the idea of graceful extensibility. This is how well can we handle the unexpected. We cannot anticipate every eventuality. Surprising things will happen. How easy or how well are we able to handle surprise? Many, many years ago, there was a BA plane flying up high above the clouds, and it flew through volcanic ash. Back then, no one was aware of the problems with volcanic ash. We knew there was a volcano, we knew there was some ash. Plane flies up high, the ash high up in the atmosphere clogged up the intakes of the jet engines, and those engines froze. No one was expecting this. The engines froze. So as a result, the pilots were like, what are we going to do? Now, luckily, the pilots descended quickly. To be fair, the pilots had no choice about descending quickly. The engines had stopped working. But they descended quickly, and that allowed them, that meant the ash actually started to thaw, so they could restart the engines. Now, in that moment, the training of the air crew and the cabin crew to keep everyone calm was key to the success of that. No one expected it, but they dealt with the situation. Right? So how well are you able to deal with surprise? And then we move on to sustained adaptability. And this is our ability to learn, typically over longer timescales. How do we learn from what happened? Because we need to take what we know and feed that back in to improve our system. And these two things dealing with surprise and learning are often when larger corporates fail. We often don't deal with surprise well because we might be given very tight role definitions. In very top-down, command and control, hierarchical organizations, you have some things that you are allowed to do and some decisions that you are allowed to make. So when surprising things happens, your organization is not set up to deal with it because your organization is effectively there to deal with the known. And when you're only there to deal with the known, your organization is not resilient, your organization is brittle. Because then something unexpected comes along and you get wiped away. An organization, though, where you've got a bit more flexibility to think differently, where you've got a bit more autonomy in different parts of your organization, you will deal with surprise better. Likewise, you need to be an organization where it is safe to learn from when things go wrong. This is a theme we'll come back to a bit later on. How easy are we able to adapt and learn from our mistakes? So planes don't fly through volcanic ash anymore. We've learned that, which is why when that volcano erupted in Iceland, air travel was grounded across large parts of Europe. So our ability to learn is key in all of this. So we've got dealing with known problems, recovering after failure, dealing with surprise, and our ability to continually learn and adapt. This is all kind of high level, and I think probably seems all very sensible. So let's now get into something which is a little bit more practical and gives you a few kind of concrete things that you could think about when you go back to work on Friday or next week if you've got some time off. So now we're going to look at resiliency in terms of reliability of a single service. And the model we're going to be using for this is something called Dickinson's hierarchy of service reliability. This is actually from work done by Mike Dickinson, who was a Google site reliability engineer, and he then went to work on healthcare.gov back in, I think it was 2013. And this cribs off Maslow's hierarchy of needs. So the idea here is that as we go up this sort of model, we kind of really want to spend time on the foundational aspects before we move to things higher up. So this covers monitoring, incident response, root cause analysis or postmortems, testing and release, capacity planning, development, and product. So in general, you kind of want to have things here before you worry too much about things up here. The reason I find this model useful is you go into some organizations and they're doing loads of stuff up the top, but they've got none of the foundational aspects in this. So it's not also saying that you have to do everything at this level before you do something up here, but if you're doing things up here and you're doing nothing down here, that is going to be an issue for you. So, monitoring. Back when Dickinson kind of coined this, that was the term we'd use. We'd now more commonly call this observability. Monitoring is something you do. Observability is a property of a system. So observability refers to our ability to understand what the system is doing based on external systems, and external signals, rather. So we'd now probably call this observability, but I'm using the original term. So if we're going to monitor things, what do we need to monitor? Most corporates I work with monitor too much and too little. So start with the 4 golden signals. For a given service, we need to measure latency, traffic, error rates, saturation. Saturation being resource consumption. That's kind of it, right? So if you don't know what you've got, if you don't know how your monitoring breaks down, this is what you need to have. Monitoring any of these in isolation of the other is less useful. We might say our service is really, really fast, our latency is looking great, and then I point out that's because nobody's using it. That's not useful information, so these 4 signals together, right? We need clarity around these things. There's some great advice around this in the SRE book, which I'll mention a bit later on. Incident response. When something goes wrong, what do? Do you have a process for how people are on call? How good are you at dealing with the troubleshooting processes or the escalation when you're dealing with a tier 1 support issue? And what about things like emergency response, communication with customers in the wake of that sort of stuff? This is something I find corporates tend to be very bad at, especially when they're moving into the SaaS world for the first time. Next, we've got post-mortem or root cause analysis. I don't like the term root cause analysis because it implies there's a single root cause, but we'll stick with the original terms. We'll talk more about that a little bit later on. So when something goes wrong, how can we learn from that and how can we improve? Now, coming back to this idea of sustained adaptability from Woods' model, we need to learn from our mistakes. So how do we know we made a mistake? This is so key. So getting a good post-mortem process and post-incident analysis process in place means, in the first instance, gathering good data about incidents and also gathering good user testimony and operator testimony. Experiential stuff does actually matter here. What happened during this incident? Well, and actually talking about how you even felt during it can be really important stuff as well. These processes need transparency within your own organization. If you don't have transparency around these things, you can't learn. Transparency is also important with your customers. So we all accept people make mistakes. It's often how they deal with it that changes our view of it. I think a lot more of those big .coms that when they have an outage, they put out a really clear post-mortem explaining what they did. And a lot of people will throw rocks. Oh, those are idiots. Those people are idiots that made that mistake in the first place. It's like everyone makes mistakes. The biggest mistake is not learning from your mistakes. A huge chunk of this, and again, this is where corporates often suffer, is if you want an effective process around post-incident analysis, you need to have psychological safety within an organization. This is mostly a cultural aspect and a corporate cultural aspect. Do you feel able to speak out? When you saw a problem, can you mention it? If you made a mistake, can you admit to that mistake? If in an organization where you've got a blame culture, you're not going to want to share mistakes. I'll come back to that idea a little bit later on as well. This is a hard thing to fix from the bottom up, unfortunately. Testing and release. And this really covers all kinds of testing. This is very much coming at things from an SRE point of view, but it covers pre- and post-deployment, functional and non-functional testing, so smoke testing, load testing, fake user transactions, and the like. Again, we're thinking about reliability. Often we're thinking about functionality. So again, these models do cross over a little bit. Next, we've got capacity planning. And again, this term is a bit misleading because people assume it just means, okay, we've got this much traffic, we've got this much growth, we need some more machines. Capacity planning isn't just about working out how many machines you need based on load. It's about making sure you still have those computing resources, even if you have a failure. So when something goes wrong, do you still have the computing resources you need? So this covers things like load balancing and failover. So this could be, how do I go, starts off multi-instance, then multi-AZ, then maybe multi-region. What is your failover strategy? Where do you want to be in that whole approach? It would also encompass things like desired state management. So systems like Kubernetes gives you out of the box to an extent, which is, if something fails, how do I replace that automatically without manual operator intervention? And might even include things like auto-scaling, although I think auto-scaling is something you should be using quite late on in this whole process, right? You can get yourself into all kinds of messes with auto-scaling. So that's really what we'll talk about capacity planning. It's like, at any given moment, even if we have failures, do we have enough computing resources that our system is still going to sustain those required operations? Next, development. And this is building our software with kind of resiliency in mind. This would extend to kind of thinking about architectures that might deal with node failure well. This would, for example, prioritizing stateless rather than stateful processing as an example, just to make node failure easier to handle. This would also include those kind of sort of engineering patterns that we need developers to understand. Things like how do we implement idempotency for any appropriate API operations, and how we handle an individual node failing. And then finally at the top, we've got product. And this is where we start thinking about how we control the rollout of new product features. So basic concepts like separating deployment from release or staged rollouts. Now again, the purpose is not that I do everything here before I do this. This is more to help us understand if I'm focusing my time up here and I've not got any of this in place, then I'm going to be missing some important building blocks. And again, just from a larger corporate kind of point of view, I find that enterprises tend to do monitoring badly, instant response badly, and post-mortems badly. They're a little bit better at this nowadays in terms of functional testing, but non-functional testing tends to be terrible, and it can all be a bit iffy. But it's amazing to me that this stuff often gets missed. And that's often because those roles are so siloed away from the people that build the software. Now, a lot of this stuff I first learned about from the Google SRE book. This is completely freely available. I'm just going to caveat my recommendations around this book. The Google SRE book has been very influential, but it is a point-in-time document of how Google did site reliability engineering when the book was written. The book was written a while ago. How they do things has changed. Also, a lot of what Google does is based on decisions that they made like 10, 15, 20 years earlier, and they could have made different decisions that also would have worked. So do not assume everything in this book is how you should do things. I see a lot of organizations copying what's in this book, and it's not healthy. But there are some really useful insights here, and there's lots of useful tidbits. And the fact it's freely available, and I want to promote it. And actually, all the Google SRE books are, so you can go read that one for free. We're going to move on now to our third model. So we've gone kind of resilience engineering as a whole. We've then looked at the Dickinson's hierarchy of service reliability, which is quite specifically to our digital systems. And now we're going to go broader again and look at the hexagonal model for socio-technical systems and try and understand how this can help us when thinking about making systems more resilient. So, a computer, relatively speaking, is quite a simple thing. I mean, I couldn't build one. I'm not that smart. But it's still, by itself, quite simple. One computer is quite simple. One service isn't too difficult to explain. But like, OK, I've got a service instance, and I've got a database on a separate computer. So I've got a little distributed system. But then we recognize that, I need multiple instances and a load balancer. So, OK, it's getting a bit more complicated now. And then, of course, this is just one service as part of a larger kind of connection of services. So now I've got lots of different services. I've got lots of hardware running. Here we have lots of hardware running in a data center. They don't look like this much anymore, right? The liquid cool stuff just looks, I don't know, it looks too sci-fi. But, this is when I used to be able to go to data centers. And we're building distributed systems across multiple, often virtual data centers. And our systems are becoming more and more complicated. All of us here are in the business of building distributed systems of varying degrees of complexity. This definition from Leslie Lamport is my favorite definition of a distributed system. A distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. And it's a lovely, because this is like distributed systems kick our asses all the time. And the more distributed they are, the more complicated they become, which is why we shouldn't be doing microservices, right? But this is just the distributed system computer part of it. But of course, we actually have people, right, interacting with the systems. And our systems exist in a wider context. And all of these all of this stuff works together or doesn't work together to make a system resilient or not resilient. Systems are messy. And even when we say a distributed system, if we're looking at it from a reliability and a resiliency point of view, we cannot look at it purely in technical terms. The distributed systems that we build and that we operate are fundamentally what we refer to as a socio-technical system. This is quite a long word. It's a bit of a management consultancy word. You've got to think I'm going to pull out a 2x2 quadrant. Don't worry, I don't work for McKinsey. Let's break this word down. Socio-technical. Socio meaning people, technical meaning technology, and technology in the old sense of the word, kind of meaning referring to sort of knowledge and doing. Okay, so this is socio-technical. So when we say something is socio-technical, we mean it's people working with technology. Okay, so that's the knowledge and doing side of technology. So in our world, that would encompass our hardware, our software, and our processes. The actual original work around socio-technical systems was done during World War II in the UK when they were using this to sort of understand how to understand coal mining. So this would be like you've got people down in the pits, like working miles underground, harvesting coal. How can we understand that system to make it safer, to make it more efficient? They recognize that you can't just look at the equipment. You can't just look at a hammer or a pickaxe. You've got to look at the whole thing as a piece to understand how to optimize that process. And so when we're thinking about the resiliency of our own systems, viewing them as socio-technical systems is a huge benefit to us. Because if we really want to understand the resilience of our system, we cannot look at the software in isolation. Because if we do, we are missing things. Coming back to air travel, thinking about it as a larger system, for example, we've obviously got the hardware-based components of air travel. We've got the engines, the jet engines. My first job was actually helping design the turbines in jet engines. I had no idea what I was doing, but I had smarter people around me, and I just made the sums add up for them, right? So making sure that our engines are designed to potentially survive things like volcanic ash or bird strikes or whatever, knowing how long they have to run between services, that's part of making air travel resilient and safe. But so is how we train the pilots and the cabin crew, because they're also key to the safety of the entire system. Making sure that the pilots are well trained to handle different scenarios, that the cabin crew can keep people calm and get them evacuated in the event of something going wrong. It's also down to the air traffic controllers and their software and their training and everything else. And so if you have a weakness in different parts of this system, that could undermine things you're doing elsewhere. So you do have to look at these things more holistically. And I've got to say, actually, we do really well with air travel. A lot of these things are also applied, these concepts are also thought about in the areas of things like sort of any safety critical system, so it includes things like hospital administration, for example. But we don't often think more broadly in the stuff we build, well, that we all build together. And I was struggling, though, to parse this concept of a socio-technical system. And again, because it's quite an academic term that comes from that world of safety critical systems, which is quite alien to me, and I suspect a lot of you. Right? Unless you work in that space for a while, it's a whole load of way of doing things and a whole lot of language that isn't familiar to you. And so it took me a while until I found a model that helped me sort of try to break down what a socio-technical system was. I came across this paper by Leeds Business School, which is where I first saw this hexagonal model. And again, there'll be a QR code link at the end to download the slides, which has all the links in the deck. This is the first citation I can see for the hexagonal model. I don't think it's the original citation, but until I find the original citation, this is kind of it. And the way this model breaks down is we've got these 6 factors. So we've got sort of, and I've kind of renamed this one a little bit, we've got software and tools, we've got infrastructure, we've got process, we've got people, we've got culture, and we've got goals. And all of these things impact each other. So on the left-hand side, we've got the socio side. This is kind of the people side. So this is our people, the culture they operate, and then the goals in which they're set. And on the right-hand side, we've got techne. This is the technology side of things. This is the process, the infrastructure, which would be our data centers and the like, and our software and tools. And this model has actually been used to try and understand what happens in the wake of failure, and also in an attempt to prevent failure happening in the first place. This work done, again, this was done by Leeds as well. Yes, it's done by Leeds as well. This was looking into trying to use this to understand what happened in the wake of a disaster, to see how things were interlinked. So this particular report covered work done in a rail derailment called Grey Rig, which is unfortunately, a person died. Fortunately, it was only one person that died in this particular incident. So they did this analysis, and they said, well, let's look at what happened. So we have a whole load of things that are kind of on the infrastructure side. So this talks about the failure, that on the face of it, if you were thinking in terms of, okay, just I'm looking for a single cause of failure, the reason the derailment happened was that there was a maintenance issue with the track, and that caused a derailment. So if that had been maintained properly, there wouldn't have been a derailment. So looking at it purely from an infrastructural point of view, there was basically some structural issues that caused a derailment. But looking deeper, they also found there was a technology piece here, that these maintenance issues weren't being properly logged. So there's problems with the system where this information wasn't being logged properly. They then found a whole bunch of processes that weren't being followed appropriately around the maintenance. And then they see there was a culture problem here. It's quite hard to see on this slide, unfortunately, but they found that there was a culture of underreporting maintenance issues. So when problems needed to be fixed, they weren't being reported as quickly and easily as they should otherwise have been. Part of the reason for this is that there was a goal in the organization that says we want to defocus maintenance because we want to modernize. So our focus is on modernization. And by focusing on modernization of the railway that undermined a focus on maintenance. So from a corporate goal point of view, you were disincentivized to report maintenance issues. And that led to people not wanting to report maintenance issues. So focus on that modernization over maintenance. That meant there was less time available for maintenance in the first place, which then led to people not doing the work, right? All of these things are kind of interconnected. And so if you say, okay, how do we stop this thing from happening? It's like, well, that track needed to be fixed. Yeah, but why wasn't it fixed? So if we're trying to bring things into fix and improve this system, looking at these items in isolation aren't necessarily going to help. I don't necessarily like using real-world examples where people died, but unfortunately, it's often in the wake of kind of major incidents like this that we actually do the analysis to find out what happened and we can learn from it. I got to apply this model a little bit in a situation I was very, very peripherally involved in. I got myself into trouble. I used to live in Australia, big telco called Telstra, and Telstra had a massive outage. And this caused internet and fixed telephony to stop working across all of Australia, and this wasn't good. I blogged about it, and that led to the trouble. So basically, for a whole day, no fixed phone telephony, no mobile telephony, and Australia is a very, very, very big country, right? Not many people in it, okay? Probably as many people in a small suburb of Bengaluru, I'm going to guess, like 24 million people, just that, right? In a massive country. So when the telephony goes down, you've got lots of rural communities not being connected. This is a big deal. And so the press are like, why doesn't the phones work? Because, again, a problem. And Telstra decided to get out a statement very, very quickly to put everyone's mind at ease. So I'm going to read the statement out, and this is what I reacted to. And it's kind of an interesting case study in how to handle things or how not to. This came from the COO of the company. So the COO said, this is a national newspaper. We took that node down. Unfortunately, the individual that was managing the issue did not follow the correct procedures. That's my emphasis. And so we've already gendered the person, so already we can start thinking about who that might be. So it's not the women that did it, it is the men. It's normally the men anyway. But we now know, because we've been told by the COO it's a man. He reconnected the customers to the malfunctioning node, what an idiot, and rather than transferring them to the 9 other redundant nodes that he should have transferred them to. So we're being told very quickly that this person made a mistake, and he's clearly an idiot because he had 9 other opportunities to do the right thing and failed to do it on all of those opportunities. This is coming out less than 24 hours after this failure happened, by the way. The statement goes on. The employee responsible didn't follow procedures, and clearly that is not a good thing. Oh, you think? But I wouldn't want to preempt the proper investigation. It seems to me like they've already done their investigation, and you've decided that this individual is an idiot for not following the proper procedures. And we haven't had a chance to dig into the detail, you think? So I responded saying a few things. That firstly, if you are a national telco with millions of people relying on you for calls, having a system where a single human being can make a simple mistake, and that takes the whole system down, do you think that's a good thing? We have to recognize that human beings make mistakes. We're good at it. Expecting human beings never to make a mistake does not seem to be a sound basis on which to build a national telco. The second thing I said is, how do you think people at Telstra are going to feel when they see a COO coming out and publicly blaming an individual? Now, they weren't absolutely named, but I pinged friends at Telstra and said, do you know who this person is? And I said, oh yeah, we've all worked it out. So that person's name is now mud in the organisation. How bad do you think they're feeling? No one feels good when they make a mistake. And now you've got the COO, your boss's 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 boss, probably, bad-mouthing you. In that environment, do you think people are going to be willing to say what went wrong? To raise issues like, oh, by the way, this is a completely manual process. Now, weirdly, despite the fact that this problem was caused entirely by one person making a mistake, Telstra kept having lots of issues for the rest of that year and kept having other outages. So either they kept putting that one person back in charge of all this, or maybe, I don't know, there were other issues going on. The COO, who was in charge of kind of the reliability of the network, was being groomed for the CEO role. They left the job within 10 months because of this cascade of failures. I got in trouble because I blogged about it. Australia's not that big a place. It got picked up by the press, and then it turned out the company I was working for at the time, well, Telstra was a customer. So I got in a little bit of trouble. But anyway, it's like, it was fun. So looking at this from our socio-technical system point of view, we've got a node failure, right? Wasn't clear if this was a software or an infrastructure issue, but there's something that's gone wrong in this space for the node to fail in the first place. We've then got a process issue. It's a manual process involved in handling the failover, and we've got a dependency on a single person. So that seems to be a kind of process-style failure. We've then got, clearly, a top-down blame culture. You heard the phrase that shit rolls downhill? That organization at this point in time certainly seems to be an organization like that, a blame culture, which led, in turn, to people not raising issues. And unsurprisingly, these issues continue to happen over and over again. So I found this model to be really useful in terms of stepping back and looking at the bigger picture to try and understand what's going on. So I've given you 3 models for thinking about resiliency. I want to leave you, just before I go on my summation, one last useful thing to think about. This is the band Chumbawamba. And they did a great song called Tub Thumping, which I still think actually, when you get down to it, is the definition of resiliency I like more than any other. And in that song, they say, I get knocked down again, but I get up, and you're never going to keep me down. This is a large amount about what resiliency is about. Resiliency isn't about saying nothing bad's ever going to happen. Resiliency isn't about saying we're never going to go down. It's actually much more about how you get back up and how you deal with it. Do you learn from that? Do you create a culture where people can learn and improve? Or do you blame people? One of these things ends up better than the other. So do go check out Chumbawamba and their band Tub Thumping. So you've looked at resiliency, sustaining required operations when expected and unexpected things happen. We looked at resiliency engineering, which is about making sure as many things go right as possible. We've then looked at Woods' 4 models for resiliency, the Dickinson hierarchy of service reliability, and finally, the hexagonal model for socio-technical systems. And on that note, just remember, if you want to improve the resiliency of your system, you first need to understand that it is a system, and looking at just one thing in isolation may not necessarily improve the things you would like. You can find out more information over my website. You can download the slides as QR code and get links to how you can read the early access version of my book. Thank you very much.
Thank you very much, Sam. Thank you. So we will have Sam do a book signing at 10:30, right? So we'll do some books that we have prepared. Sam also will be giving a workshop on Friday, right? So still time to sign up, but there is quite well attended already. In France, where I come from, we have the story about the reed and the tree, and with the wind. The reed bends but doesn't break versus the tree that is really strong, but when there's too much wind, it breaks and it's over, right? So be a reed, not a tree, right?
Yes, exactly right, exactly right. Yeah.
Yeah, thank you very much. So we have like a 5-minute break, and then we will have the opening. And Naresh, if you can begin to start. Come with me. We have time for 2 questions, if that's fine.
Okay, we have time for a couple of questions.
We have time for 2 questions.
Has anyone got a question for me? Don't be shy.
Yeah,
there's a question in the middle. One of my glamorous assistants will be whisking a microphone to you.
Yeah, good session. Thank you.
You might need to put the microphone a bit closer.
Yeah.
There we go. Perfect.
Yeah, cool. Good session. Thank you, by the way. So I have a question around. We think everything as a system and figure out too many problems, and which can increase the complexity, as you already mentioned. So is there a framework or something where we draw the line, right? Things can go overboard, right? Like too many. See, my system and a volcano can break out, and I'm solving for that right now. So do we have a framework, or do you have any suggestions around that?
So to stop us going too far, you think?
Correct.
Yeah. Honestly, it starts with having a conversations with the users and the business stakeholders. And I think as technologists, we think in terms of latency and traffic and error rates and failover. These are very technical things. but they don't have any meaning without a business context. So you actually start with the business. You say to them, what needs to be true about this system? What has to work? Start very much from a business outcome point of view, and then you can have a conversation with your stakeholders, because then it might be a trade-off. They might say, well, we need this to happen, and we never want these things to fail, and then you can go away and say, if you want that, it's going to cost you this much money to implement, and then they go, oh, that's expensive. What about this instead? There's going to be some horse trading, but you just start at the beginning from the business requirements point of view. And this is where I do think the SLA and SLO model can be useful. So having business objectives defined in terms of service level objectives, things that are actually then measurable, that's the way to go. But start from the business point of view, because that's going to tell you what those required operations are. Cool.
Yeah, we have another question here. Oh.
There we go.
Thank you so much. That was a very insightful session. Just to the lines you have explained the model, what all we should consider, basically while considering the resiliency into the systems. But any preference in terms of what tools we should opt for implementing these into this?
I'm struggling to hear you. My hearing's not as good as it used to be. Sorry, can you say again?
Okay, let me just reiterate it. So basically you have explained the different models, right? What we should be considering while we are looking into stabilizing the resilience into our systems. But is there any preference in terms of what tools we should be using to implement those? Do we have anything on that from your experience? Yeah?
I mean, there are some tools that I'll give you some quick ones. They're not magic solutions, but these are technologies that I would use quite commonly. So around observability, using open telemetry in my software, a good open standard, vendor agnostic. This helps me get that monitoring out that we had at the kind of towards the bottom of that Dickinson hierarchy. So open, anything that supports OpenTel, then you can use different vendors. Good systems that do desired state management. So you can use things like kind of Puppet, Ansible, those sorts of things in a continual loop model. GitOps if you really want to, but you don't have to go that far. Kubernetes gives you this. So Kubernetes does that thing where if a node fails, it will re-provision a replacement node for you. And these are technologies, just off the top of my head, that are things that I would commonly use to kind of deal with that low-hanging fruit around those things. So those would be kind of the building blocks. And these are things that I'd nearly always recommend for people if they're building, say, a cloud-native system. Is that helpful?
Yeah, thank you so much. I think some of these we are already exploring, but yeah, good to know the other options as well. Thank you.
You're welcome. Thank you.
We have one question here. Yep, please.
Hi, Sam. Thank you for the session. So oftentimes it looks like that people think that the uptime is equals to the resiliency, right? Which I feel is not true, right? Uptime of a system doesn't denote that how resilient it is. And I feel resiliency is not an IT problem. It's a business one.
Yeah.
How do we influence, from a system design point of view, to the business people that we bake in resiliency from the beginning? Because sometimes, the number of users that you're going to cater could be small in the beginning. And business doesn't, want you to spend a lot of time in making it resilient. But how do we do that? How do we influence that decision at an enterprise level? What do you think? What are the key points, 3 key points you think could help?
A lot of it comes down to communication. Like as techies, we'll have conversations about, okay, so you will go to stakeholders, so what sort of 99th percentile response time are you looking at for this service? And like that's useful measurement to us. And they're like, what? What is a response time? What's a percentile? What's latency? So I think we actually need to go and have a conversation using their language and their understanding. So firstly, understanding their priorities, like how fast this need to be. And they go, fast. And I say, can we just work that out? Like if it happened within a second, would that be all right? Okay, yeah, great. So we can use like more sort of maybe basic and not as technical language to get a starting point for that conversation. And we can then go away and interpret that into things that we can then measure in our systems. I think also as we build a system, we will encounter trade-off decisions that they might not be clear about. So like I've got a service here that communicates with a service over there. We recognize the service I'm talking to might not be available. So maybe that thing isn't there. What do we do in that situation? We can make technical trade-off decisions, but that's actually going to ask the business stakeholder, right? So if I'm about to take payment, but we're not sure if the item is in stock, what would you like to happen? Right, ask the business stakeholder. And they might then say, okay, well actually if we don't know if it's in stock, we probably shouldn't take payment and ask them to come back later. That's a perfectly valid business decision, but guess what? From a technical point of view, we've just had a conversation about cap theory, but we didn't have to ever mention the word cap theory, right? So for me, it's always about actually understanding the context as business stakeholders, and understanding what they want from an end user point of view, using that more simple language, not simple language, but business language. It's not simple to us as techies. We have to learn their language, knowing the domain helps, and that's where it starts. And then you just have to have that, it's the conversation, the communication piece really, it comes down to.
Thanks.
You're welcome. Cool.
We good?
I think we're good.
Perfect. Thank you very much, Sam, for that keynote. I think it was extremely insightful, and I think it starts the day with really the big picture about building resilient systems. Thank you very much. We can have an applause for Sam. Yeah, thank you.